Our next speaker is Sarah Brauner from the University of Minnesota. She'll be talking about a type B analog of the Whitehouse representation.
Yes, thank you. Thank you for the opportunity to talk. I'm sorry that I couldn't be here in person, but today I'm going to be talking about a type B analog of the Whitehouse representation. So the big idea of this talk is that I want to take some type A story that brings together combinatorics, topology, and representation theory, and I want to generalize that story to type B. Okay, so this is the precise type A story right here. And I don't expect you right now to understand what this picture is saying, but the goal of my talk is to explain this picture and then to tell you about my contribution, which is to generalize that picture to type B. Okay, so what I'm going to do is I'm going to first tell you about the symmetric group or type A representations that I'm interested in, called the Eulerian representations. And then I'm going to topologically interpret those representations, okay? And then I'll do the same thing over in type B. I'll tell you about the type B representations or hyperoctahedral representations that I'm interested in, and then I'll interpret those representations topologically. Okay, and so the story really begins with the symmetric group, and in particular, with a permutation, which I'm thinking about in one-line notation, and its descent set, which is the set of indices where I'm thinking of sigma I as bigger than sigma I plus 1. Okay, and so I claim that each descent set actually gives an integer composition of n, which I'm going to call the shape of sigma, okay? And I'll just show you how that works with an example. So here's my permutation of S in S5, and I can see that here 5 is bigger than 3, so that tells me I have a descent at position 2, and 4 is bigger than 2, which tells me I have a descent at position 4, okay? So the way that I get my integer composition is I draw a line after each descent, and then I look at the parts between each lines. So I'm shading them in here. This tells me that my composition is going to be 2, 2, 1, because I have a part of size 2, 2, and 1. Okay, so the statistic, it turns out, defines as subalgebra of the group algebra, the symmetric group, which is called Solomon's descent algebra after Solomon. And it's spanned by elements whose sums of elements with the same descent set, or equivalently the same shape. So for example, here's S3, the group in S3. Here are our 4 possible integer compositions, and here are the corresponding elements of the descent algebra. So the important thing is if 2 permutations have the same shape, I have to take the sum of both of them. Okay, and so sort of the upshot here is that I have some combinatorially defined subalgebra of the group algebra that's indexed by compositions, or its basis is indexed by compositions of n. Okay, and so intuitively, when I want to understand an algebra, one thing that you can do is study its idempotents or elements E such that E squared is E. Okay, and so this was done by Garcia and Reutenauer. For the descent algebra, they defined a complete family of orthogonal idempotents, which I'm going to write as E lambda. So they're indexed by partitions of lambda. And I'm not going to define them because it's a little bit technical, but the idempotents that I'm interested in are going to be a coarsening of these idempotents. So they're called the Eulerian idempotents. And the way that I'm going to get them is by summing over these finer idempotents where the partition is a fixed length. So my idempotents will be indexed from 0 to n minus 1. For example, in n equals 5, here's how this coarsening works. So for example, this one with k is 2 is the sum of the 2 idempotents indexed by partitions of length 3. Okay, and so these Eulerian idempotents satisfy a really nice generating function, which was also proved by Garcia and Brauner. It looks like this. And if I were to expand this generating function out, in the case, for example, of S3, I would get these 3 elements of the descent algebra or the group algebra of Sn. Okay, so these are my 3 Eulerian idempotents in the case that n is 3. And I'm going to be thinking about representations of the symmetric group here. So to make sure that we're on the same page, I'm thinking about my irreducible representations as being indexed by partitions of n. And when I'm talking about an irreducible, I'm just going to write the Young diagram corresponding to that partition. And I'm going to use the fact that the symmetric group has really nice branching rules. So in particular, ways to restrict representations from Sn plus 1 to Sn. So the way it works is I take my partition, lambda, and I remove boxes in all possible ways so that I still get a partition. So for example, here, this is my representation of S3. If I want to restrict it to S2, I noticed that I could remove this box, which would give me this partition, or I could remove this box, which would give me this partition. Okay, and so I take both of them. That's my restriction. Okay, so the symmetric group representations that I'm interested in are generated by these Eulerian idempots. I'm going to call them the Eulerian representations. And the way that I get them is by thinking about this idempotent, the ideal that this idempotent generates in the group algebra. So a nice special case of this is when k is 0. This is exactly describing Lie n, the multilinear component of the free Lie algebra. It's a very famous representation. And so let's see what these look like in the case of S3. We saw before that this k equals 2 idempotent here looks like this. So it's an unsigned sum of every element of S3, right? And so if I think about the ideal that it generates, if I multiply a permutation by this element, it's just going to rearrange the terms in my sum, but it's not going to change the idempotent. So in other words, the representation that I get is the trivial representation, which if you're familiar has a partition shape that looks like that. Okay, and the other two are a little bit harder to see, so I'm just going to tell you the k equals 1 case is a sum that looks like this, and then the k equals 0 or Lie case turns out to be this irreducible. Okay, and so you might notice that altogether these give me the regular representation of S3, and that's going to be true in general. I'll get some sort of decomposition of the regular representation. Okay, so the property that I want to talk about today that these representations have is that even though I've defined them as representations of Sn, there's a way to encode or lift them to representations of Sn plus 1. So to formalize this, I'm going to say a representation V of Sn has a lift to Sn plus 1 if I have some Sn plus 1 representation, let's call it W, that restricts to V. So the way that I think about this is W has all the information that V has and then some additional information as well. Okay, and so a preview of what I'm going to say is the Eulerian representations have a lift. And so I'm not going to define it precisely, but I'm just going to tell you that this lift was discovered by Sarah Whitehouse. And she showed that these Eulerian representations, each of them for each k, they have a lift, which I'm going to write as fk, and I'm going to call this the Whitehouse representation. So for example, here are S3 Eulerian representations. I want to think about what are the representations of S4 that restrict to these representations. So in the k equals 2 case, it turns out that the S4 representation is this, because if I remove this box, I get that partition, okay? The k equals 1 case looks like this, because I could remove this box to get that partition, or I could remove this box to get this partition, okay? And then the k equals 0 case turns out to be this. Okay, so these are my S4 Whitehouse representations. So just as a warning, that example was maybe a little bit simplistic, so it's not necessarily true that any representation can be lifted. So you could think about this representation here of S4 cannot lift to S5. And even if a representation does lift, it's not necessarily unique. So for example, this trivial representation of S1 could lift to this or to that representation of S2. Okay, so it's a sort of subtle property. All right, so to recap what I've said so far, I started with this combinatorially defined algebra called the descent algebra. And then I defined idempotents in that algebra. And I said those idempotents generate representations, and those representations have this interesting property that they lift from Sn to Sn plus 1 representations. But from what I've said so far, I've sort of given you very little intuition about why this lifting is happening in this case. And so that's what I want to do now. And the way I'm going to do that is using topology. Okay, so in particular, the topological space that I'm interested in is called the ordered configuration space of R to the D. So D here is the dimension of my Euclidean space. I'm going to write it like this. So I'm thinking of this as a set of n points. So each of these xi's lives in R to the D. And I'm just going to require that they're distinct. So for example, if D is 1, let's say I take n to be 3, it's just the set of points in R3 where each coordinate is distinct. I could draw this as a picture, right? It's going to be the complement of these 3 planes, which are the planes where 2 of my coordinates are the same. And maybe this picture is familiar, or if I project along this line where the planes intersect, I get this picture, which is the rank 2 braid arrangement. And in general, the D equals 1 case is going to be the complement of the braid arrangement. Okay, so a very natural question you could ask is, what is the cohomology of this space? And this has been answered by Arnold and Fred Cohen. So here's the presentation, and I don't want to dwell too much on what it looks like. I just want to note three things. So first of all, even though we're thinking about this for a general D, it turns out that the presentation only depends on the parity of D. So I'm going to get like an odd presentation and an even presentation. Okay. The next thing is that this cohomology ring, it turns out, only has n non-zero graded pieces. Okay, and then the last thing is that the symmetric group acts on this underlying topological space by permuting coordinates. And so that tells me that at the level of cohomology, I'm going to have an SN representation on this ring. Okay, and this actually gives us the sort of key connection between these two things that I've talked about. So the key connection here is that each Eulerian representation is isomorphic to, as a representation, to the graded pieces of this cohomology, this configuration space, in the case that I'm in this odd setting. So this was originally deduced by character comparison. So Phil Hanlon computed the characters of this side, and Sunderman Velker computed the characters of this side, and you can check that they're the same. I later proved this in the context of Coxeter groups. So this was the topic of my FIBSAC 2021 talk. Okay, so here's an example for S3. This part of the picture is not new. We've seen this before. The sort of new part of this picture is that each of these representations here is describing the pieces of a cohomology ring. Okay, so we now have sort of two ways of thinking about our SN representations. You can ask, is there a way to understand the lifts of those representations, so the Whitehouse representations topologically? And so that's what I want to do next. And to do that, the idea here is I kind of want to add a point to the space R to the D. So that's going to give me a D sphere. And in particular, I want to think about the case when D is 3. So I have the 3 sphere, which is homeomorphic to SU2, which is the group of 2x2 matrices that have determinant 1. Okay, so we can take a configuration space or form the configuration space on SU2. And this n+1 here is telling you that somehow this is going to help me get my lifts. Okay, so this is a set of points, P1 through Pn+1. They're in SU2 and they're distinct. But now SU2 is going to act on this space diagonally by multiplication because it's a group. And so the space that I'm actually going to care about is the quotient by that diagonal action. Okay, so this might look like a sort of strange space, but if you think about a typical point, it helps. So here's a typical point if n+1 is 4. But because I'm quotienting by this diagonal action, I can multiply through by P4 inverse and get an equivalent point that has 1 as my last coordinate. And the idea is that I can do this in general. So a typical point in this space is going to be the set of points Q1 through Qn, where I'm going to require, okay, Qi is not equal to Qj is not equal to 1, and then 1 as my last coordinate. So intuitively, I can't draw a 3 sphere, but if we pretend we're in the 2 sphere case for a second, I'm just saying that I'm picking n distinct points on the sphere, and I'm not allowed to pick the North Pole. Okay. So the reason to study this space is that it has two very natural actions. One is by Sn+1. So this space is comprised of n+1 tuples, and I can permute the coordinates. Okay, so that gives me an Sn+1 action. But I can also think about the restricted action using this typical point, right? So I can just permute the first n coordinates and leave the last coordinate fixed. Okay. So I want to use this to relate this quotient space to the original configuration space that we started with, which we know is related to those Eulerian representations. And the way that I'm going to do this is via stereographic projection. So I was picking n points over here, not allowing the North Pole. I might as well stereographically project and pick n points over here. Okay, and so this actually defines a homeomorphism. So what I do is I'm going to take a typical point here, and I will stereographically project the first n coordinates, okay? And then I'm going to forget the last coordinate, okay? And so I claim that this defines not just a homeomorphism, but an SN equivariant homeomorphism, because I can permute these points, and that's the same thing as permuting these points. Okay, so the upshot here is that this homeomorphism really tells us that this space is the right one to consider if we want to think about both an Sn and Sn plus 1 action. So the Sn action here is the same as the Sn action on our original configuration space, but this quotient space makes clear an Sn plus 1 action that was far from obvious on this original space. Okay, so when we move to the level of cohomology, functoriality is going to tell us that this Sn representation carried on the pieces of this cohomology ring of the configuration space of R3 will lift to an Sn plus 1 representation on this other configuration space cohomology. Okay, so we now have two different lifts, and you could ask, are these lifts equivalent? And the answer is yes. So this is work of Eulerian and Brauner, who proved sort of exactly what you hope would be true is true. In other words, that this isomorphism of Sn representations has a lift to Sn plus 1 simultaneously. So these Whitehouse representations are exactly describing the graded pieces of this cohomology ring. Okay, so this is now gives us our complete type A story. Some other key features that I'm sort of sweeping under the rug is that there's a recursion that relates these Eulerian and Whitehouse representations. So one determines the other. And there's also on the topological side, some really beautiful connections to equivariant cohomology that sort of deepen this story. Okay, so this is the type A story. And what I want to do is generalize this to type B. So basically, I'm thinking of this as a signed version. So all of the type A objects that I've been thinking about, permutations, partitions, integer compositions, will become signed versions. So we'll have signed permutations as our group elements, signed partitions, and signed compositions. All right. Okay, and so to find a type B analog here, the first step is that I want to generalize this first part of my story where I started with the Eulerian representations and I lifted them to the Whitehouse representations. And really the first thing I have to do there is find a generalization of Solomon's descent algebra. And it turns out in this case that the right generalization is called the Mantaci-Reutenauer algebra. So it's a subalgebra of the group algebra of Bn. Again, it's combinatorially defined in a very similar way to the descent algebra, and this time it has a basis indexed by signed integer compositions, okay? So compositions that can be positive or negative. Again, we have orthogonal idempotents that decompose this algebra. So this is due to Monica Bazzarani, who showed that the Mantaci-Reutenauer algebra has these orthogonal idempotents indexed now by signed partitions, okay? And I'm going to do the analogous thing that we did in type A, that I'm going to coarsen these primitive idempotents by summing over certain ones. So in particular, I'm going to sum over the positive part of the partition that has a fixed length. Okay, so this is going to give me n plus 1 idempotents indexed from 0 to n. And what you should think is that these G lambdas are generalizing my E lambdas. And these GKs are exactly generalizing my Eulerian idempotents in type A. Okay, so again, I can think about the representations generated by these idempotents as the ideal that they generate in the group algebra, okay? And so a sort of preview theorem of what I'm going to say is that each Bn representation generated by these idempotents in the Mantaci-Reutenauer algebra has a lift to Bn plus 1. But really, to understand where those lifts are coming from, we have to turn to topology again. Okay, so this is the last thing I want to do is I want to find some sort of type B analog for this topological story I told you about the cohomology of this configuration space lifting to the cohomology of this sort of more complicated quotient configuration space. So when we move from type A to type B, the objects in type A were configuration spaces. Now we're going to think about Z2 orbit configuration spaces, which I'm going to define via an example. Okay, so the orbits we're thinking about here are Z2 orbits. So we're thinking about the action of Z2 on SU2, or the 3-sphere, via the antipodal action. So pictorially, this looks like sending, the North Pole to the South Pole. Algebraically, this is like sending P to negative P. Okay, and so I can define this Z2 orbit configuration space on SU2. It's the set of points P1 through Pn plus 1. They're all in SU2. And this time I'm going to require that PI is not equal to plus or minus PJ. Okay, so that's where that orbit is coming in. And this n+1 is telling me somehow this will get at my lifted representations. So again, SU2 is going to act diagonally on the space, and I can quotient by that action. Okay, and I can again think about a typical point in my space as, okay, it's going to be QI is not equal to plus or minus QJ is not equal to plus or minus 1. Okay, and then 1 as my last coordinate. Okay, so intuitively what I'm saying is, all right, I want to pick n points on the sphere. I'm not allowed to pick the North Pole. I'm not allowed to pick the South Pole. And if I pick a point, I can't also pick its antipode. Okay, so there's some more conditions, but it still makes sense. And again, we have these two very natural actions. So we have a full action of Bn+1 on the space because the space is comprised of n+1 tuples. And then so now I'm going to permute and negate my coordinates. Okay. Or I could think about this restricted Bn action where I'm permuting and negating just the first n coordinates here, okay, and leaving that last one fixed, okay? And so I want to use this, this sort of the same idea that we saw in type A to obtain sort of a description of this quotient space as related to a genuine orbit configuration space, so not a quotient. And I'm going to do it in the same way via stereographic projection. So I have to be a little bit careful here. So in type A, I was saying, okay, remove the North Pole, which is fine when you stereographically project because that's what you do. Here, when I'm thinking about points in my space, I was saying I can't pick the North Pole or the South Pole. So what that ends up being under stereographic projection is that I can't have 0 in my set of allowable points. So that's not a big deal. What's a little bit more subtle is that we have to be careful about this antipodal action. So in SU2, the antipodal action was just sending P to negative P. But once I stereographically project, I get a weird scaling factor. So Q is going to go to negative Q over its magnitude squared. So I still have a Z2 action over here, but it's just a little bit strange. Okay, so nonetheless, we have sort of a parallel story. So this was the homeomorphism that we got in type A, relating this quotient configuration space to the configuration space of R3. And in type B, we get a very similar homeomorphism. So here is our quotient orbit configuration space. And I'm saying that it's homeomorphic to a Z2 orbit configuration space on R3, which I'm going to write like this. So this is a set of points P1 through Pn. Each of these PIs is in R3, but not 0. And they're distinct. And I also have that PI is not equal to the image of PJ under that antipodal Z2 action. Okay, so to give you some intuition for this space, if you remember in type A, when D was 1, this configuration space was just the complement of the braid arrangement, right? In type B, this configuration space here is not the complement of hyperplanes anymore, even in the case that D is 1. So for example, this is what the n equals 2, D equals 1 space looks like. So you can see that I'm taking the complement of some lines, but then I'm also taking the complement of curves.
Sarah, can you take about 2 or 3 more minutes?
Yes.
Thanks.
All right. So the theorem here is that this topological space and these representations coming from the Mantaci-Reutenauer algebra are exactly what we want. So first, we have an isomorphism of Bn representations. So these representations coming from the Mantaci-Reutenauer algebra are exactly describing the Bn representations on the graded pieces of this cohomology ring. The second thing is that this Bn representation has a lift to Bn+1, where it's being described by the cohomology of this now quotient orbit configuration space. All right. And then we have analogous recursions that relate the sort of Bn representations with their lifted Bn+1 representations and analogous connections to equivariant cohomology on the topological side. Okay, so in summary, here is our type A story, right? We started with representations coming from a combinatorial algebra. In type A, it was the descent algebra. And on the topological side, we had the representations on this configuration space cohomology. And then we said that those representations lifted to Bn+1. All right, and then in type B, we have these our representations that are coming from a combinatorial algebra are coming from the Mantaci Reutenauer algebra. They're isomorphic to the representations on the cohomology of this orbit configuration space. And again, they lift to Bn plus 1. Okay, so this is sort of this lifting is a very subtle property. So I think a natural next question is to really understand where and when we get lifts, generally, especially in the context of Reith products. All right, thank you.
Thanks. Thanks for a beautiful talk. Any questions? Is there any hope of doing this in other types? I know the Reith product is a natural place to look, but type D or something?
I think type D is also a reasonable hope. And sort of, I think we understand very little about this like lifting property. It's very subtle. And so I think like even in the symmetric group, we don't understand really when it happens. So I think that in general, like we could expect that there are representations of Dn that lift to Dn plus 1. Yeah.
Mm-hmm. Any other questions? Sorry, Sheila.
Yeah, hi, Sarah.
Hi.
I just wondered, what made you think of doing it with Z2 orbits? Was that just a natural sort of thing?
So originally, when I was trying to generalize this picture, I started on this side and I was trying to find a lift of the Bn Eulerian representations, which wasn't working. And I think I proved to myself that they couldn't lift. That was like an impossible task. And so then I sort of decided to work more on the topological side. And then I think from there, when you're thinking about like topology and you want a Bn representation on the cohomology, you really want to look at a Z2 orbit configuration space because there's a natural like I'm really thinking about Bn here as the Reith product of Z2 with Sn. And so in general, like if I have a configuration space like this, I'm going to have an action by G Reith Sn. So that's sort of where the Z2 is coming from. But the fact that, so yeah, but I think I also originally tried to start here, which wasn't working. So I think this sort of worked, but yeah, so that, I don't know, did that answer your question?
Yeah, yes, thank you.
And I guess like the recursions actually helped me. So I said that there's recursions that relate these representations, and actually that's a result of looking at a fiber sequence. And so I think that sort of clued me in to thinking about this space here.
Great. Any Per?
So are there combinatorial formulas for how these representations decompose into irreducibles?
No, so this is an open question even like in type A. We have no idea how these like Eulerian representations decompose into irreducibles. We can describe them in terms of plethism. And I think in the Lie case, there's a nice way of understanding it using a major index of Tableau, but that sort of is because Lie overlaps in other contexts. So I think in general, we don't understand these, and we also don't understand these as irreducibles. I think we can also describe them as induced representations, but not into irreducibles.
Okay, any other questions? Let's thank the speaker again. Thanks, Sarah.